like you guys to type that in. Y equals 2 to the x. Oops. Y equals 2 to the x. So the x is the actual exponent itself. So you get something that looks like that. Okay. Now, what I'd like to do is just kind of walk through this, go to your table. I'd like to walk through with you guys what is actually happening in this graph. So when you're looking at the table, you've got y to the 2x. That means you've got 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, 2 to the 0. When you have negative exponents, does that mean the base is happy? No. So that means this is 1 over 2 cubed, which is 1/8. This is 1/4, 1/2. What is anything to the 0 power? 1. And then you get 2 to the first, 2 squared, and so on. And then 2 cubed, 8, and so on. So what's happening here, if you go back and look at the graph, will this curve ever cross the y-axis? Excuse me, the x-axis. No, it's never going to cross the x-axis. So it'll get infinitely closer and closer and closer to it, but it doesn't touch it or cross it. What is the x-axis called right now? When you get closer and closer to something, but you don't cross it or touch it. It's an asymptote. Very good. So you've got an asymptote here. All right. Now, with these exponential growth, or when we get into exponential decay problems, you will always have asymptotes. You'll have some value that the curves are approaching, but they're never quite going to get there. There are rules of how you find that. It's quite simple. So what we're dealing with here is, well, real quick, what is the y-intercept? Go back to this. What was the y-intercept of this when you look at your table? 1. The y-intercept is 1. The y-intercept number means x is 0. So the y-intercept here is at 1. So here's what's going on. You have this graph in the form, you have y equals 2 to the x. There is what we call a generic form. The generic form of these equations is a times b to the x. In y equals 2 to the x, what's the value of a? 1. Good. So it's the same thing as saying 1 times 2 to the x. Yeah?
Is it possible that 2 can also be a to the 17?
No. Yes, because it's raised to the x. If 2 was a, it would be 2 times 2 to the x. The b value is always the one that's raised to the x1. Always. So what happens here is that you have, this is the general, or if you want to call it the parent form for exponential growth problems. Your y-intercept always will occur at the value of a. Always going to occur at the value of a. It always occurs at a. And where is the horizontal asymptote always with the parent function? It's always at y equals 0. It's always the x-axis. All right. For the parent function, your asymptote is always at y equals 0. Okay. Remember, it's always horizontal, left, right. Okay. Now, from these types of graphs, then, what you're going to be able to do is identify where your y-intercept is for your parent. What does it look like via your table? And then that just means all we have to do is add in your shifts. Okay? We're going to add in some shifts. So here's what it looks like as we go on. Well, let's do this one first. When I have the function y equals 1/2 times 3 to the x, first thing I'm going to identify is my a value, my b value. A is 1/2, b is 3. So that means that my y-intercept is 1/2. It's always the value of a. Remember, the reason that the value, the y-intercept is the value of a, when you have a y-intercept, what is x equal to? 0. Anything to the 0 power is always 1. 1 times 1/2 is 1/2. So I know right away without having to do anything, I have a y-intercept at 1/2. We okay with that so far? Now, here's what you do. We go to our graphing calculator, and we type in the equation. When you have fractional parts in your calculator, do you guys still use fractions, or do you use 0.5 or something easy like that? Either one is fine. It doesn't really matter. When you have a fraction that is easily simplified out, like 1/2, 1/4, if you want to use 0.5, it's no big deal. So it's 0.5 times, was it 3? 3 to the x. Oops. Graph it. So we know it's going from left to right. So go to your table. And I'm just going to kind of dump my table onto here so we can work with it. You guys have them in front of you. Okay. Now, as you look at this table, it's giving you some pretty gnarly looking decimals, isn't it? All right. Well, at -1, it's 0.1666, whatever. Okay. -1, it's about here. Does it have to be perfect? Well, I'm pretty close. Just a couple. Couple, 2, 3, yeah. Whatever's easy. I mean, because what's going to happen depending on a lot of these things, as you get more and more into this 0.018, really? Yeah. It gets to be kind of, that fudge factor shows up. So that. I think it's just exponentially smaller or larger, whatever. At 1, it's 1.5. At 2, it's 4.5. And at 3, it's off the chart now. Okay. So for all intents and purposes, you get something that just looks like this. Okay. You just plotted a couple of points. And as we get into this a little bit further, we have to put our shifts, all the shifts in. We'll have to make sure we label some of them. But like I said, when you're doing these things, you have a table on your calculator. You should be okay to plot some things. Oh, graph you guys. Grab 2 sheets of this as it's coming around. That way you guys have one for notes and then one for homework tonight.
That every section of chapter 8 uses graphing in a separate section.
There's like one of them that doesn't. I think it's the last one. So then let's worry about a different a value. What's the a value now? Very good. Your a value is -1. Good. So now my a value is -1. My b value is 3/2. So when I go to my graphing calculator, to type that in, y equals, clear it out, -1 times parentheses 1.5 to the x, close it. Remember, there's many different ways you can type this fraction in your calculator. For time's sake, I'm using 1.5 because it's 3/2. The calculator's going to do all the work for me. You guys have the function on your calculator to change to a fraction itself. My operating system in the computer does not do that. That's why I changed some stuff around a little bit differently. but it's still going to look the same. Now when I graph it, is it going up and right? It's going down and right. Right. And the only reason that is because it's a negative value. It's a negative a value. So exponential growth could still be, it's going to go either up and right or down and right for exponential growth. Exponential decay is going to go left and up or left and down. Okay, that's going to be the only difference between growth and decay. So don't freak out if you see a negative a value. You still do the same stuff. You still want the same values. You still have to hit your table function to get your things. Your y-intercept is still at -1 because your a value is -1. When it's -1, it's at -2/3. It's getting closer and closer, so it's going like this. Then at 2, or at 1, it's 1.5. At 2, it's 2 1/4. So it's just going like this. I'm dropping down. Yeah.
For a lumber graph, do you want us to try converting a graph, or do you want us to just like do a couple?
A couple on both sides for right now, especially for the ones that don't have a shift involved, is perfectly fine as well. It's perfectly fine. Okay. Because now the next slide I show you is going to have the shift. Okay. The next one's going to have a shift. But remember, H's and K's haven't changed. When you shift something, an H value, is it moving left or right, up or down? H's, they go left and right or up and down? Left and right. K's go which way then? Now, remember, horizontal, vertical. So you get this. The shift. So what happens here is now that we have moved things left and right, up and down, we no longer have the asymptote at y = 0. The horizontal asymptote moves to whatever your k value is, always. So if your k, remember the rules for h's and k's. Since it's x minus h, if in the equation it said x plus 3, what's your h value? -3. It's the opposite sign of what you see. Your k value, does the sign change? K values, the signs don't change. So when you go to graph these things, just like we graphed cube root functions and square root functions, the first thing you're always going to graph is the parent function. So let's look at an example and what to do. So I have the example of y = 3 times 2 to the x minus 1 minus 4. So anytime I've got a problem like that, what I'm going to do is label out a, b, h, and k always to start with. Okay? I'm always going to do that. So what is my a value? B, h, k. Good. So now that I've done that, I'm going to plot the parent function. Your parent function is always going to be a times b to the x. So in this case, it's going to be 3 times 2 to the x. That's the first thing I'm going to plot. When I plot that parent function, do you guys remember where the y-intercept is for the parent function? 3, good. So the parent function, my y-intercept is at 3. And then I'm just going to go to my calculator and put in y = 3 times 2 to the x. Oops, one button.
Is it possible to graph both lines at once and see like how those?
Yeah, just use the second line of the graph. Absolutely.
Will the table take second line or the
You have to jump between the lines. You just have to select the line, that's all. So in this case here, once again, I know, and this is like Jake, you were saying, how many points should I put on here? Now, when I'm looking at this table, I'm just going to pick, you know, 1 or 2 on the left and 1 or 2 on the right. So we know that for the parent function, 0, 3, negative 1, 1.5, negative 2, and 0.75. And I know it's doing this. And then at 1, it was 6, 2, and 12. So it's doing this. And yeah, sometimes not all of these are going to fit on your graphs completely perfectly. That is the parent function, correct. Now, what do you think I have to do to each one of those points? Shift them. What am I shifting? I'm going to the right one and down 4. So for each of these points, if you have a change of color, that'd be perfect. I know that my asymptotes can be at negative 4. There's my asymptote. So I start with any one of them. Is it okay to shift points that are fractional amounts? You just got to be careful with them. They're not that difficult to move around. As long as you're close, it's not that big a deal. So I go to the right 1 and down 4. Right 1, down 4. Right 1, down 4. Right 1, down 4. Right 1, down 4. 1, 2, 3, 4. And there's my new curve. Okay? And let's say you have forgotten everything about shifting left and right via the points themselves. Could you type that into the calculator and get the table? You can still do that. It'll still work. All right? But I want you guys to see how this thing shifts. Just like they've shifted all throughout the school year so far. With every AH and K that we've worked with, the shift still works. Okay? So hopefully it's not too scary, to tell you the truth. Most people tend to believe as you get into most of the AHs and Ks, it's really not that bad. All right. I'll try one? All right. This one's try. We start with A, B, H. A is 1, B is 2, H is 3, K is 1. Do you agree? Okay. So when I go to plot my parent function, I know my y-intercept is at 1. At 1, it's 2. At 2, it's 4. At 3, it's 8. So that means at negative 1, it's at 1/2. Something like that, correct? Yeah.
Yeah, I've been graphing it wrong. I keep taking the entire thing to get the actual function instead of just the parent function.
Yeah.
So, when you're just taking it to the parent function, it's just the y equals
Whenever you have that H and the K tagged in the equation, always plot the parent function first.
Okay.
And then show the shift. So I know that this is what it's going to look like as we go. All right. So for these points then, each one of them has to move to the right 3 and up 1. I know that my new horizontal asymptote is going to be at the value of K, so it's going to be at 1. So I'll move everything to the right 3. 1, 2, 3, up 1. 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 So my new one looks like this. And there we go. Yes. Yes. Always show your horizontal asymptote, guys. Always show the horizontal asymptote for your shift. Yes, ma'am.
your parent function gives us the asymptote, not the real one?
The parent function, oh, the parent function, you don't see it. The parent function is just there so you know where did it move to. Okay? The parent function has its own asymptote at y equals 0. Okay? So the parent function has its own asymptote at y equals 0. Don't worry that you see it crossing it here. It's not that big of a deal. It's just showing the shift. Okay, so it's just moving over. If you want to even consider it, you think about if we have that, I have that starting asymptote there at y equals 0. If I move the asymptote over 3 up 1, where'd the asymptote go? To the new asymptote. So everything is being moved up and over. Yes, sir.
How do you know the asymptote?
Asymptotes for the parent or for the shift?
Like you said, you have to put it on.
The parent function, the parent function is always at 0. The shifted function is always the value of k.
Okay.
No, not a. It's just at k.
Oh, so that the asymptote is just a k?
Yeah. Yeah. Y equals k is always your asymptote. Always, always, always. Okay. When you get into a couple of these things, you'll see that the graphing part is relatively simple. But there's two parts to this chapter, or to this section. You've got the graphing part, and then you've got the growth model part. Ooh. Exponential growth models. This is kind of like the precursor to a whole bunch of word problems. But remember, when you're dealing with these word problems, that they're going to give you a formula. You just have to know what parts mean what. That's all. And they're all basically the same. So what you have here is this exponential growth model. It starts out y equals a times the quantity, 1 plus r, all raised to the value t. Let me explain to you guys what each of these parts mean. A is always an initial amount. Whether it's going to be money, population, whatever. R is some percent as a decimal. So if I say it's 15%, what is that as a decimal? 0.15. Okay. And then T is always time. And usually it's in years. Okay? It's usually dealt with in years. What they'll do here is they're going to take this part here, 1 plus r. They call that the growth factor. And let's say we have the following parts. Let's say you have $500 for an initial amount. Your percentage was 15%, and we'll say time is 2. Let me show you what that looks like when you substitute it all in. When you substitute all that in, you wind up with the following. 500 times 1 plus 0.15 to the 2. Bless you. And what the book does is that they're going to write it as 500 parentheses 1.15 squared. They take that 1 plus the rate right away, and it's written as 1.15. Sometimes they'll ask you, what is the percentage? They give you 1.15, what's the percent? Yeah, 15%. Yeah, you just subtract 1. That's all it is. Okay. And then later we talk about decay. It's going to look the same, but it's going to be rate minus 1. Then you flip it around on it. Okay. So you just it's very simplistic. Okay. So this formula is used in a lot of times in stuff that looks like this. Population models. And you might have seen stuff like this in many different classes. The population of Winsamula, Nevada. It's a joke. Get it? Winsamula, Nevada, Las Vegas. Winsamula. It's not funny, please. Don't humor me. Don't try to humor me. You don't get extra credit. Anyway. Poor Isabella, she's like, but there's no L.
Isabella, even I got that. You're supposed to be smarter than me.
So here's what happens. You've got, instead of some value y, they're saying p for population. The population is 6191 times 1.04 to the t, where t is the number of years since 1990. So let's say you wanted to figure out what the population was in the year 2000. What would t have to equal? 10. That's the kind of stuff you have to do, right? See how it says population from 1990? If I say what it is in 2000, figure out what t is, how many years have elapsed. What was the original population? What's the initial amount? 6191. Your initial amount is 6191. Okay, that value of A, the initial amount. What's the percentage here? 4, not 0.4, 4%. Because it's 1.04, and like I just said a second ago, when they add them together to get your growth factor, that means this is the same thing as 1 plus 0.04. So your percentage is 4%. Okay? That's the kind of stuff we're looking at. Yeah. Yes, but a lot of times what they do is they give you the formula. They're going to give you the formula. They'll give you the exponential growth formula, especially for compounding interest, which we're going to talk about next. More often than not, the ACT, when you have to use a formula, they give it to you. If it's not something that's used all the time. So if you signed up for that ACT prep class, sign up for it. Because I know I think there's... Never mind. If you have, I think they still have a sign up available down by Mrs. Maney. I know that they're doing one here. All right, so it's reminding people to sign up for it. I do the math part, so you get to see me twice in one day. Exciting. All right. So I forget what I had here. So yeah, see how it works out to be the same formula?
I thought we were using circles for
And here's what you're saying about ACT for compounded interest. A lot of times you will get the formula. It may not look exactly like this one, but they will give you a formula that you just have to decipher what goes where. And econ? Yeah, I heard. Are you guys using the P-E-R-T one? P to the E-R-T? Because I show you that one in a couple of days.
E1 plus R lambda N.
You're using the same one.
Yeah.
All right. So once again, that p-value is the principal. It's your initial amount. I always spell initial wrong. Your R is your rate. It's percent as a decimal. N. N is where things change. When it says N stands for number of times something compounds. So when you have things that are compounding, you have to know what the differences are in compounding. So if it's annual, how many times does annual mean? 1. If it's semi-annual, it would be twice. If it is quarterly, if it's daily, what if it's daily with a leap year?
6. What?
Now, once again, the value of t is usually time in years. And more often than not, they're going to give you most of the information. Okay, they're going to give you most of the information here. So you're going to see stuff like the following. And I've got the formula on the next page as well, so I will walk through this again with you. I'll actually take it with. you're going to be given stuff like this, where you have $1,000 in an account that pays 8% annual interest. Find the balance after a year if the interest is compounded with the given frequency. In other words, blah, 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 blah. 4. P equals 1,000. Your rate as a decimal is how much? Rate is a decimal. 8%, what is it? 0.08. Now, for A, if you're compounding annually, what is your value of N? 1. For B, what is your value of N? And then C? What is your value of T for all 3 of them? 1, because it tells you what's the balance after 1 year. So what you wind up with here are 3 problems that the only thing that changes is your N. So you wind up with 1,000 times the quantity 1 plus 0.08 over 1 to the 1 times 1. You just got to be careful how you type in your calculator. In this instance,
Oh, yeah.
all I'm doing is substituting it. Okay. In this case here, you've got divide by 1. That means it doesn't do anything. Raise anything to the first power, doesn't do anything. So for part A, all you have to do is 1,000 times 1.08. $1,080. Yeah.
Are we going to have to put, what do we call it? Labels? I don't think so, like 1,000? Yeah, units on it, that's what we want.
Oh,
So when we have to put like.
that?
Yeah, well, we have to do that on like tests and homework and stuff.
How many times have I forgotten to label things?
It was.
No, I know. I'm not going to be, I don't think I'm going to be that big of a jerk.
Okay.
At least today. How about this? If you're dealing with population, can you have half person? So just watch it for what you're rounding, okay?
Alright.
In part B, we have 1,000 times 1 plus 0.08 divided by 4 to the 4th power, because it's 4 times 1. So when you type that in your calculator, suggestion that I would give to you guys is just type it slowly. Be careful. I don't mean like going. Just watch what you're doing, okay? Break it off into easier chunks. More often than not, you guys will go too fast when you type that in. So what I would do, if I were you, because I'm running a little short on time here, in my calculator, I would do just the parentheses part first. 0.08 divided by 4, add 1. Okay? Raise it to the 4th power. Times it by 1,000. And there's my answer.
Whoa.
$1,080.43. What I'm doing here is I'm working on the inside out using my order of ops. Instead of trying to type it all in there as one long string, that's usually where people screw up. Okay? There's your answer. You're dealing with money, so you have to put it with rounded to 2 decimal places. All right? So I know we ran a little short here, but I'd like you to do these tonight. All right? Put this down so I get this to load.